Section 1 in Chapter 7 is on action-reaction forces, or forces and interactions. And the big idea is that a force is always part of a mutual interaction that involves another force. And so in the simplest sense, we've defined a force as a push or a pull. And when we say there's a mutual interaction, it means that we have two different objects or things that are interacting with each other. For instance, if this guy is going to push on the wall, he's going to exert a force on the wall by leaning on it. The wall also exerts a force back on the person. A hammer that drives a nail. Hammer drives the nail. We would also say that the nail halts the hammer. The nail exerts a force on the hammer, so as it hits it, the nail stops the hammer. So a hammer exerts a force on the nail, drives it into the board, and there must be also a force exerted on the hammer that stops it. So Isaac Newton's the one who, again, came up with this idea, and he reasoned that while the hammer exerts a force on the nail, that's pretty obvious from the situation, the nail also exerts a force back on the hammer. And so we have an interaction, and there's a pair of forces, one acting on the nail and the other acting back on the hammer. So we see that forces occur in pairs and interact with each other. And this leads us to Newton's third law, which states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force back on the first object. So this is called Newton's third law, and it simply describes a relationship between two different forces in an interaction. One force is called the action force, and the other force is called the reaction. So you hear a lot about action-reaction pairs in physics, and this is what we're talking about is Newton's third law, action and reaction forces. Neither force exists without the other because forces always occur in pairs. They're equal in strength and opposite in direction. Remembering forces are vector quantities, and so equal and opposite means that they have the effect of canceling each other out, and they occur at the same time, which means they occur simultaneously. All right, here's the way Newton's law is often stated, is that to every action there is an equal opposing or equal and opposite reaction. It really doesn't matter which force we call action and reaction as long as we understand that they occur in pairs. So here's a couple examples. If you push against the floor simultaneously pushes against you. So if you stand up on the floor is pushing back. We would actually call that the support force. We've been talking about that in class. The tires of a car interact with the road to produce the car's motion. The tires push against the road, and the road actually simultaneously pushes back on the tires. When you're swimming, you push the water backward, and the water pushes you forward. So again, you see, we're talking about what two things are interacting. It's you and the water. It's the tires and the road. It's the floor and your feet. So again, we see two different objects or things, items interacting. And that's how we identify action and reaction forces. The interactions in all of the examples that we just talked about depend on friction. If a person's trying to walk on ice where there's not very much friction, you may not be able to exert that action force against the ice. You've all probably experienced that in the winter around here if you get a slippery sidewalk or you're out on a pond that's frozen. You would see that it's difficult to exert a friction force because ice is fairly frictionless. So we see without an action force, you can't have a reaction force which would result, and so we don't have any resulting motion from that interaction. So here's kind of a picture. When this girl jumps to shore, the boat moves backwards. So she's pushing on the canoe to get onto the dock, and the canoe's pushing back on her, which allows her to move forward, but the boat moves backward. Another weird way of thinking about it is that the dog wags its tail, but the tail also wags its dog. So the dog exerts a force on its tail, and the tail also exerts a force back on the dog. So one of the tricky parts with this idea with Newton's third law of action-reaction forces is actually being able to identify which is the action force and what is causing the reaction force. So in order to do that, the third section of your chapter talks about identifying pairs of action-reaction forces. So first you identify the interacting objects, and then the action A on B and B on A. we'll talk here about what that actually means. All right, so here's a simple recipe for treating action and reaction forces. First, you identify the interaction. So say you have one object A somehow interacting with another object B. And so the action-reaction forces are stated in the form. The action is object A exerts a force on object B, and then the reaction is object B exerts a force back on object A. So A on B, and then B on A. Sometimes it's not as easy to identify, and sometimes the action-reaction forces are not quite as obvious as some of the examples we've been giving. So for example, let's talk about a case we've been talking about with a falling boulder, like a boulder in free fall. So what would be the action and the reaction? We would say that the action, Earth exerts a force on the boulder. We'd say that force due to gravity would be the action force, Earth pulling on the boulder. And then the reaction is simultaneously that the boulder actually exerts a force back on the Earth, which we don't think about too much, but when you start to think about Earth pulls the boulder toward itself, the boulder actually also pulls the Earth toward itself just a little bit. Here are three action type of forces. The action on the first one up here is that the tire pushes the road. Okay, we have the tire on the car pushing the road. Second one, we have a rocket moving forward, and so the rocket pushes the gas molecules out. And the third one, here we have Galileo dropping his ball off the Tower of Pisa, and Earth pulls the ball toward itself. So those are all action forces. And here's the reaction forces. So the reaction, you just kind of switch it around. The action in the first one, the tire pushes the road. The reaction would be that the road pushes the tire. Second one, the rocket pushes the gas. We switch them around. The gas pushes the rocket. Third one with the falling boulder, the Earth pulls the ball, and the reaction would be that the ball actually pulls the Earth a little bit. So go ahead and try to answer this question on your own as you're thinking. We know that the Earth pulls on the moon. Does the moon also pull on the Earth? And if so, which pull is stronger? All right, section 7.4 is that we're going to talk about action and reaction, how it affects different masses differently. So if we have a given force, the main idea here is a given force exerted on a small mass produces a greater acceleration than the same force exerted on a larger mass. So let's go back and talk about the Earth and the boulder a little bit more. So we see that Earth is pulled up by the boulder with just as much force as Earth pulls the boulder down. Those are equal and opposite. This is according to Newton's third law. Again, we have an action force, Earth pulling the boulder down, a reaction force, the boulder pulling the Earth back up. So we see that the forces are equal and opposite in direction, equal in strength, opposite in direction according to Newton's third law. So we say the boulder falls to the Earth. We see that, we observe that, but the Earth actually falls to the boulder, but the distance the Earth falls is much, much less. So small, in fact, that we don't even notice it. So why is that? It has to do with the Earth's mass. Okay, Earth has a huge mass compared to a very small boulder. So if we have a picture of the Earth up here and we have just a teeny boulder falling toward it, the action, here's my boulder, it's falling toward it. The Earth is pulling it with a force toward it, and the boulder is pulling the Earth back toward itself. But the fact that the Earth is so much more massive than the boulder means that the Earth doesn't move, or it has an infinitesimally small acceleration. This means very, very small acceleration. Another good example to think about is that when there's a cannon fires a cannonball, there's an interaction between the cannon and the cannonball. Again, we have an object A and an object B. So the cannon exerts a force on the cannonball, and it's exactly equal and opposite to the force that the cannonball exerts back on the cannon. You might expect the cannon to kick more than it does, but the cannonball moves very fast compared with the cannon. So according to Newton's second law, we also have to take into account the masses of these things. So here's the cannon. It shoots the cannonball out, and the cannon moves back. Action force over here, cannon on cannonball, reaction, cannonball back on the cannon. So the cannonball undergoes much more acceleration than the cannon because its mass is smaller. If we take a look here in this animation, it says when the cannon is fired, there's an interaction between the cannon and the cannonball. The force the cannon exerts on the cannonball is equal and opposite to the force the cannonball exerts back on the cannon, so it kicks. And here's a picture of that. Play it one more time. You can see that when the cannon shoots the cannonball launches out of there very quickly. The cannon also moves back, but not as much. And the reason for that is that this cannon has a much larger mass than the cannonball. It's kind of the same thing as the earth and the boulder that we were just looking at. Here's one more time. Cannonball shoots out with the force from the cannon. The cannonball exerts a force back on the cannon, and that causes it to kick back. If any of you have ever shot a gun or hunted or anything, you've experienced a kick from the gun, and you see that this is true. So here's a couple of equations that kind of describe this. F represents both the action and reaction forces. In this case, you'll see that these two F's both have the same size, okay? And the M that is big is the mass of the cannon. So here is the mass of the cannon, two ends there, cannon, and this is the mass of the cannonball. Okay, and so what we see is when we take a force and divide it by a very small number, we get a bigger acceleration. Versus over here with the cannon, if I take that same force and divide it by a much larger mass, I get a smaller number, a smaller acceleration. And so we can see why the change in the velocity of the cannonball is greater. Again, this is actually an application of Newton's second law, force equals mass times acceleration. And we can extend this same idea of the cannon recoiling for the cannonball to understand how rockets work. And so if I have a balloon, we blow air into a balloon, and the balloon recoils from the escaping air, okay? So air pushes out of the balloon with a force, and the balloon pushes the air out. The air pushes the balloon back, and that's what would shoot the balloon forward. So it accelerates as the air comes out. A rocket works in much the same way. It continually recoils, kind of like a balloon, from the exhaust gases ejected from its engine. Each little molecule of gas is like a tiny little cannonball shot out of it. So the rocket will shoot out the air. Here's a little picture of a rocket. Okay, all the air shoots out. The rocket shoots the air out with a force. Each of these little air molecules, gas molecules, will push the rocket forward, and that's what causes the rocket to accelerate. A common misconception is that rockets only work when there's air present, but we see from this idea that really it's the interaction between the gas and the rocket itself that causes the rocket to move forward. So both the rocket and recoiling cannon accelerate because of the reaction forces, not because of air. In fact, it's true that rockets actually work better where there's no air because there's no air resistance to stop the rocket or slow it down. And so again, the rocket recoils from these little molecular cannonballs. The rocket pushes them out. Each of those little gas molecules pushes the rocket back, and what you get is the rocket moving forward with an acceleration. So using Newton's third law, we can understand also how a helicopter gets its force, its lifting force. The whirling blades force air down, and that same air forces the blades upward, and this upward force is called lift. When the lift equals the weight of the aircraft, so we get enough air pushing back up, the helicopter actually hovers in midair, and when the lift is greater, the helicopter climbs up. It depends on which force is greater. Birds and airplanes also fly because of action and reaction forces. If a bird is soaring, the shapes of its wings deflect air downward. The air again with the reaction pushes back up, and so the bird flies. The slightly tilted wings of an airplane do the same thing. They also deflect air downward, and the air pushes back upward and produce this effect that we call lift of an aircraft.